Okay, so now we're going to look at the mean value theorem, which we're just going to call MVT from here, because it gets really irritating writing mean value theorem over and over and over. Okay, so once again, if, let's say, f of x is continuous on a closed interval and differentiable on an open interval, then there exists a number C that's somewhere in between A and B. Such that f prime of C, clean up that one a little bit, is equal to f of B minus f of A all over B minus A. All right, now if we were going to look at that as far as a graph, say we draw our x and y axis.
B minus f a,
Hmm?
right? F of B minus f of a.
Yes. Clean that up some. It's a little bit close. F of B minus f of A. Here we go. Okay, so let's say we have some random graph here. Doesn't have to be straight, any crooked looking graph. Let's say we have our value A here and our value B there. Okay, that means this point would be A f of A, and this point would be B f of B. Add up a little bit. So if we wanted to find the slope between those 2 points, we just use our f of B minus f of A all over B minus A, or y2 minus y1 over x2 minus x1. And if you remember, that is just the slope of the secant line. So they're saying that somewhere in between there's a point where if you pick that value of C, that slope is exactly the same as this one. Now, the C could be here, it could be here, it could be here, it can be anywhere in between the two. But at some point, if you pick it, this, your f prime of C, will be equal to that. All right. Any questions on that one? All right, so let's say, for example, let's say if we want to find the value of C in the interval 7, 9, guaranteed by the mean value theorem for f of x is equal to -7 times x minus 9 squared. Straighten that out a little. Okay. So that means as long as it's continuous and it's differentiable, then there's some f prime of c that's equal to the slope of the secant line. Okay. So we know that f of x equals -7 times x minus 9 squared is continuous and differentiable. Well, it's continuous on the closed interval, which is from 7 to 9, and the open interval from 7 to 9. So we can use the mean value theorem. Okay. That step isn't necessary, but it's one of those things where you just to make sure you understand the actual concept first. Okay. So what we want to do is we want to find f prime of c and f of b, well, instead of b and a, say f of 9 minus f of 7 all over 9 minus 7, and make sure they're equal. To solve for c. Okay, so that's the goal there. So the first thing you have to do is find our f prime of c. Oh, might as well see f of c, which is -7 c minus 9 squared, which means our f prime of c, we're going to bring down our 2, so -7 times 2, subtract 1, and since we're going to do the inside, it would just be 1 anyway, we just leave it like that. So we know f prime of c is equal to -14 times c minus 9. Okay, so that's the first part. Second part, we have to find our, let me go ahead and write it out, slope of the secant line, which is equal to f of 9 minus f of 7 all over 9 minus 7. And I'll do that on the side here. Okay. So f of 9 is equal to -7 times 9 minus 9 squared, which is just 0. And f of 7 is equal to -7 times 7 minus 9 squared, (7 minus 9 is -2. -2 squared is 4. -7 times 4 is -28. Okay, so we know this is going to equal f of 9, which is 0, minus -28 over 9 minus 7, which is 2. Okay, so you have 28 over 2, which is 14. Okay, so we know our slope of the secant line equals 14. Okay, so to find our value of c, our slope of the secant line has to be equal to our tangent line. So f prime of c equal to the slope of the secant line will just give you negative 14 times c minus 9 equals 14. Right. Does that make sense? All right. And then we just solve for c. So if we divide both by negative 14, we end up with c minus 9 equals negative 1. And if we add 9 to both sides, c is equal to 8. Okay. So that's the point where your slope would equal 0. All right. Any questions on this one? All right. Leave that up for a few seconds. Okay, so now we're going to cover the extreme value theorem. And absolute extrema. An extrema is just a fancy way of saying minimum and maximum values. Or if you have your, where the slope is equal to 0, those are called your peaks and valleys, as they call them. Uh-oh. Okay, so we know that, let's say that f is defined on an interval, let's say from A to B. Yeah, let's say from A to B. Okay, if some value c, is the minimum of the graph, f of c is less than or equal to f of x for every value of x. So no matter what value of x you plug in, that c value is going to be either less than or equal to that point. Or that y value is going to be less than or equal to. Or might as well say every. So for every x. Okay. And the opposite is true. F of c is the maximum of f of x if f of c is greater than or equal to f of x for every x in the interval. So if we looked at that as far as a graph, let's say if we have our X and Y axis, let's say our endpoints are closed circles, and our point C is a closed circle. Sometimes the light makes it look like it's open. So this would be our minimum, which is our f of c. And that's our maximum. Okay, and also, let's say if we have that same graph, but instead our endpoints are open circles, and our C is a closed circle. Okay, why does that one look like it's not shaded in, and that one does look shaded in? All right, now this one actually does have a minimum value, but it doesn't have a maximum value. Because let's say that open value is 5. That means that you can get as close as you want to 5, but you just can't equal 5. So you can make it 4.9, 4.99, 4.999, 4.9999. You can just keep on going closer and closer. So it's never going to equal that, so there is no actual maximum value. And same thing, I'll draw that right here. Should have enough room. X and Y. Let's say our endpoints are shaded in, but we have an open circle at the bottom. Okay. Now in this case, you actually have a maximum, but you don't have a minimum. And again, it'll get closer and closer and closer and closer and closer to that value, but it won't actually reach it. All right. So for this one, this will be your f of c, because every f of x is lower than that. Oh, actually, my f of c should have been up here. And this should have been my c. All right, any questions on that one? All right. Okay. Do that up for a few more seconds.
Last graph, what you're saying there is the f of c, or you say that f of c is the maximum on that last graph, and you say no minimum?
Yep, it's no minimum because it's an open circle. Yep. All right. Now for this one, if you want to say C1 and C2, you could, just to kind of separate the two. so let's say, for example, oh, actually, we have to go over the, make sure, yep, the actual definition of the extreme value theorem. Glad I looked down. Which we'll just call EVT from here on out. Once again, extreme value theorem gets annoying to write over and over. Okay, so again, let's say that f of x is continuous on a closed interval and differentiable on an open interval. And they're saying that if those two ideas are met, then it absolutely has an absolute, well, not absolutely, then it definitely has an absolute maximum and absolute minimum. And the absolute maximum is just like the name suggests, it's the absolute largest y value. And absolute minimum. Which is the smallest y value. Now, absolute minimum and absolute maximum are different from local minimum and local maximum, because you can have multiple local minimum and maximum. That's anywhere the derivative is equal to 0. So those would be your local minimum and maximums. But when you have that absolute, out of all the minimum and maximums, the complete largest and smallest are your absolute minimum and max. All right, so let's say, for example, let's say if we have f of x equals cotangent of x. Let's say on the interval of pi over 4 to 3 pi over 4. Okay. So we can say that this is guaranteed to have an absolute maximum and minimum. And this is how we can figure out why. Okay. We know that cotangent of x is equal to cosine of x over sine of x, which means the sine of x can't equal 0. Which also means that x can't equal 0, can't equal pi, can't equal 2 pi, can't equal 3 pi, so forth, so on and so on. So x can equal 0, pi, 2 pi, etc. Okay. So since we know that, between 0 and pi, that's where pi over 4 and 3 pi over 4 are between there. So it's actually continuous in between there. So cotangent of x is continuous between pi over 4 and 3 pi over 4. And it's also differentiable everywhere between there. You just have to use the product rule and you can find the derivative. Okay. So since it is continuous and it is differentiable, we know that it has an absolute minimum and maximum. And plus, if you plug in your two endpoints, they exist. And is guaranteed. By the mean value theorem to have an absolute minimum and maximum. All right. Any questions on that one? All right, so let's say if you have one f of x equals 1 over natural log of 3x on the interval from 1/4 to 2. Oops, bring that up a little bit.
In the top example, did you mean to say that cotangent of x was guaranteed to have an absolute minimum and an absolute maximum by the EVT instead of the MVT, or did you mean MVT?
Oh, EVT. Yeah, thank you. All right, so for this one, you actually know that it's not guaranteed to have an absolute minimum and maximum, simply because natural log of 1 is equal to 0. We know that this can't equal 0. So x can't equal 1/3. 1/3 is between 1/4 and 2. Not right in the middle, but it's in that interval. So 1/4 is less than or equal to 1/3, less than or equal to 2. No, actually, I should have put that as not continuous. So it means the function 1 over natural log of 3x is not continuous on that interval. So that means it's not guaranteed an absolute maximum or minimum. So absolute maximum, absolute minimum. By the extreme value theorem. Now, that's not saying that if you change the interval, it wouldn't be guaranteed 1. Now, if you change the interval between 1/2 and 2, since 1/3 isn't in that interval, then it would have an absolute minimum and absolute maximum. So that's just for this interval. So if the interval changes, then the results could change also. All right, any questions on that one?